you have this matrix here, it's 2 by 2 matrix of complex numbers, whose determinant is non-zero, then we can define the corresponding Mobius transformation by this, okay? So you can see there's a one-to-one correspondence between this matrix and the Mobius transformation. So what you want to show is that T sub A composed with T sub B is equal to T sub A times B. So let's see. So T would be the Mobius transformation, right? Like that. So here's what, I'll just show you what you need to show, okay? And then you guys can do it. So here's what you need to show. So let's suppose that T, so we can do a T sub A. And maybe that will be A1Z plus B1. And then C1Z plus D1. And then if you have a T sub B, okay, T sub B of Z, then you can make that A2Z plus B2, and then C2 over C2Z plus D2. Okay, so what you need to do to show this is the following. So then also, okay, hold on. So also, you have corresponding matrices. So this A matrix corresponds to these coefficients, and the B matrix corresponds to these coefficients from the second one, so the 2s. Okay, now if you multiply A times B, are you guys familiar with matrix multiplication?
Yes.
Should you want me to review it a little bit? Because maybe that's the problem. Okay, so when you multiply these two matrices together, these are both 2 by 2 matrices, so you're going to get a 2 by 2 matrix as a result. But for this first, so you have 4, so 1, 2, 3, you got 4 slots in the matrix. And in this first slot, it's the first row and the first column. That means you're going to go to the first row here and the first column there. Multiply A1 times A2 plus, and then you have B1 times C2. That's the first slot, okay? And then the second slot right over here, that's the first column. I mean, that's first row and second column. So you go first row here and second column. That would be for this slot here. And so you got A1 times B2. And then you have, then going across to here, you have B1 and then going down to there, D2. And D2. Okay, and then you just get these two slots here, right? You get those two there. Now, T sub AB, A times B, this is A times B, is going to be, just put this coefficient in there. So it's A1, A2 plus B1, C2 times, wait, I don't need the, no, it's not a matrix. I don't know why I put that there. Okay, so Z plus the second spot here. And then divided by, and then you put these guys, and then you put these guys down here. Okay. Whatever is in the matrix goes there. And that's this part right here. Okay, now for this one, you take the composition T sub A of T sub B of Z. So you compose these two functions. You can compose these two functions and figure out what that is. And that answer there, you just make sure that that answer is equal to this answer, and then that would do it. Okay. So I'm not going to go further with that. I'll let you guys finish that off if you haven't already. But that's what you need to do. You have to show, this is going to be something, and then show that that's with the results equal to this. It looks kind of complicated, a lot of places to make mistakes. But it shouldn't be that hard. Okay, so what other questions do you have before we continue along? Any other questions on the homework?
Sorry, I came late. Did they ask any question?
So only ask number 10. But yeah, you can ask a question.
Can you give us more hints on number 5?
Number 5?
5.
This one?
Like where to start?
Okay. So what you do is if you take a Mobius transformation, so this is the key right here. So you just take the Mobius transformation, it's going to be like this: AZ plus B over CZ plus D equals Z. So you're going to solve that, right? And that gives you, let's see, if this goes over this side, you have CZ squared plus DZ, right? So get everything to one side equal to 0, leading off with the CZ squared, and then use the quadratic formula.
Okay.
And maybe it's some little conditions, because it can't be that it's different than the identity map. So the identity map is where you have f of z equals where it's just z. So A is the identity map. So what that is it's a Mobius transformation like this, except A has 1, B is 0, C is 0, and D is 1. So it's just basically T of z equals Z. Okay. So everything's a fixed point when it's with the identity map, because it's just everything maps to itself. Okay. I wanted to also say a few things about number 9. Has anybody attempted to do number 9?
I did, but
A and B.
I had a question.
Yeah.
Like for part A, do we just show that AD minus BC is not 0?
Yeah. So just identify A. So say, okay, A is 1, B is negative A, or say maybe quote. Maybe you could say like, quote, A is 1, B is negative A, and C is negative A bar, and then D is 1, right? So it's like that, and then just go AD minus BC is not 0. Okay. And then the inverse, just use the formula for the inverse that's earlier. Okay. What about part C? Anybody have any problem with part C?
Is that just so like 1, 2, 1, then on 2 by like?
Yeah. So this is all Mobius transformations are pretty much this, as long as A. Yeah. So that part you don't have to worry about. so much, so you don't worry too much about that. The main thing is showing that it maps the unit disk to itself. That means it maps this to this. Okay. And so I just wanted to point out that the way you can do that. Okay, so let me go to the next page here. So this is 3.9, number C. Well, what the heck? What am I doing? Number C. 3.9 or 9C. I guess I could just say 9C. So 9C. So you're given this one right here. Right? And it's an obvious transformation. So you want to show that it maps the unit disk onto itself. Let me make sure that's what we have. Yeah, so that's the one. Okay. Oh, they also say that the modulus of A is less than 1, but you can just kind of, I think if you ignore that, it doesn't matter. I think you're still good. I don't think that really comes into play here. Okay, so you want to show that F maps the unit disk. So we'll write down onto itself. Okay. So really, there's only two things you have to do. Okay, the first one is to show that F maps a point inside to inside. Okay, and that one, 0 is a point inside, right? And if you put a 0 in here, you're going to get negative A. And which is less than 1. Okay, so you do need this part. Okay, you need that part. It's less than 1 because modulus of A is less than 1. So that part, that pretty much does the first part. Okay, then the second part, you can show that it maps modulus of Z equal to 1 to equal to 1. So if you can show that the boundary maps to the boundary point, the boundary maps to the boundary, then you're good that way. So any point that whose modulus is 1 maps to another point whose modulus is 1. Okay. So let me show you now to do this, to show this right here, you don't actually have to show it for every single point. Okay, so this point right here, so this set right here is just the unit circle, right? And you want to show that it maps it to so this is the XY plane, and this is the UV plane, and this is the variable W. You want to show that this circle maps to that circle. Now, you don't have to take every single point and show that every single point maps to there, okay? Because Mobius transformations map circles to circle or a line. You just need to show 3 points from this one map to W equals 1. Okay, and these can be any 3 points. Okay, so now the easiest ones to choose from typically are going to be there's 1, there's I, there's -1, and there's -I. So those 4 points are typically going to be the easiest to choose from. Okay, so when you're doing this, or let me just show you the first one. If I choose 1, for example, what's f of 1? We'll take the modulus. What's f of 1? If we put a 1 in here, what do we get? What's the numerator?
Would it be 1 minus a and 1 minus the conjugate of a?
Yep, I'm going to say it 1 minus the conjugate of a.
And then a, because a is 0, so it would be 1.
Well, a is, well, this is where it was 0 here, but in general, a is, we'll say a is c plus di. How's that?
Okay.
Okay, so let's let a be c plus di. So then this is going to be 1 minus c plus di over 1 minus the conjugate. What's the conjugate?
C minus di.
Yes, perfect. Okay, so this is going to be 1 minus c minus di for the numerator. And the denominator is going to be 1 minus c plus di, right? And then because the modulus splits up like this, so the modulus of a quotient is equal to the quotient of the moduluses. Okay, so what's the modulus of this? The numerator. It's the square root of this first one squared plus the second one squared. And then down here we have the square root of the first one squared plus the second one squared. And then those are equal, so that's going to be 1, right? Okay, so we've showed it for the point 1. And then, so what you need to do is choose a second point and a third point. I would choose -1 for your second point. And then take f of -1, show what this equals to, and eventually you should get 1 because you get something like this. And then for your third point, I don't know, you can choose I or -I. Or something else, but it has to be on the unit circle. Okay.
For the a part
So,
though, that I just choose, for example, maybe f of 1/2.
for the A part, the A part's all done. Because
Oh,
we already know that 0, we already know that, okay, so basically, it's like this. If this point maps to somewhere inside here, if this point in the inside maps to the inside, then everything inside is going to map to the inside. Okay?
so it doesn't have to
Wait.
be the center, Just any point inside.
Yeah.
Okay.
Yeah. Okay. Let me say that. Let me say that again. Okay, because I didn't quite say the truth there. If this point maps to the inside somewhere on the inside, I don't know where, it maps there, it might map there. You know, it turns out that it maps to negative a, right? But negative a could be anywhere, because like if a is like maybe 1/2 plus a half I, then it's going to map to negative 1/2 minus a half I, right? So it's gonna take 0 and map to negative a, wherever that is. But we know that that's modulus less than 1. Okay, so that means it's inside the disk here. Okay, now if that happens and the boundary, this boundary here maps to this boundary, okay, then everything inside has to map to everything inside, and it's going to be 1-to-1 onto, and so bijective. Okay, so if something from this side maps to the other, so if this circle here maps to this circle, there's 2 options. Okay, the first one is that this point here maps to somewhere inside, in which case everything inside will map to everything inside. The second case is this point right here maps to somewhere outside, in which case everything inside maps to the outside, and everything outside will map to the inside. Okay, and that would happen if modulus of a were greater than 1. That's exactly what would happen. This inside would map to the outside. Okay, so there's just 2 possibilities, and you need just to confirm which one it is.
What
okay, because what's that?
in line?
If this maps to a line.
Mm-hmm. No. Is there any possibility that a line
Yeah,
to it?
for this right here. A line can map to a circle, and a circle can map to a line under a Mobius transformation. But with this particular Mobius transformation, this circle is going to map to itself. Okay. Now the points are going to get rearranged along the circle. So like f of 1 is going to be 1 minus a over 1 minus a bar. But that point is still going to be on the circle because its modulus is 1. Okay. So this point here, this point right here, it might map to maybe that point there. Okay. And then this point here might map to another point, like there maybe, and so on. But so essentially, you just need 3 points. Okay, because this is a circle, and if you figure out where 3 different points map to, then those 3 points are going to either form a circle or a line. So 3 points will define a line. So if you have if the points are collinear, then that's going to be a line. But if you take 3 points on a circle and you apply a Mobius transformation, and those 3 points are not on collinear, then those 3 points are going to determine a unique circle. There's only one circle that goes through 3 points, right? So if you have 3 points, there's only one circle that goes through them, through all 3. So if you can take 3 points here and show that they map to 3 points on this circle, then this has to be the circle. Then this circle has to map to that circle. Okay, great. Let's move on. We defined here let me look it up. Okay, the exponential function. Okay. Okay, so we're defining the exponential function here. And it's an extension of the exponential function for real numbers. It's e to the, so if you think of it this way, so you can think of exp of z. Okay, think of it as exp of x plus iy. But then if you think of it this way, it's raised to the x plus iy. I think the idea, the reason they don't just define it this way, oh, it's e raised to this power here, is because they want to kind of get away from the idea that it's just this number raised to a certain power, okay? Which, if you're looking at the laws of exponents, you know, e to the x plus iy is equal to the e to the x times e to the iy. That seems to be what makes sense with the laws of exponents. So, but they don't want to try to go that route, so they call it exp, just to kind of avoid saying that it's e raised to something like this. Some textbooks will actually define it to be the series from n equals 0 to infinity of z to the n over n factorial. And if you remember in second semester calculus, this is actually the series. If you replace that with an x, this is exactly the series for the exponential function, right? For e to the x. E to the x would be this, if this was an x. Okay, now, of course, this part, this e to the iy is cosine y plus I sine y. That's certainly true, and that's exploitable. Another thing that you should notice here is that this is kind of like, this right here is kind of like a polar form. Okay, so remember polar form is like r e to the I theta, right? So, but this is polar form in that with e to the x being r, so r is e to the x. And the theta, this theta here is just equal to y. Okay, so that's kind of an interesting thing. Now we have all these properties here, A through F. And you don't generally, when someone says periodic function, what comes to mind? Just curious. Does anything come to mind? Does you have like, oh, a periodic function? Does some particular function come to mind? For anybody? Okay, so periodic means that f of z plus t, we'll say t, is equal to f of z for all z.
Sine, cosine, tangent.
Yeah, sine, cosine, and tangent. Those are the main things that people think of when they say periodic function. Because the sine just goes like this. It just kind of, it's just a way of going along. So is the cosine. And tangent does a weird thing, I don't know, with asymptotes, but it just repeats itself forever. Okay. Now, people don't generally think of the exponential function as a periodic function, because exponential function just, it starts really low and then goes up like that. It just goes out of control like that, right? So you got an asymptote, boom there, like that. So people are like, no, that's not periodic. And yeah, if you're looking at just the real numbers like this, then of course this is not periodic at all. But it's actually periodic because of this guy right here. And the period is 2 pi I is the period. Okay, so yeah, because if you have a, so this is your angle form, right? The angle part of the polar form. So if you increase this by 2 pi, then you're going to stay the same. So if you increase the y by 2 pi, then you're going to get the same value back. You're going to get the same values back for this and this. Okay, because cosine and sine have a period of 2 pi. That means that this is going to have a period of 2 pi I. Okay. Which the y, okay, so the y, again, the y axis is the imaginary axis. So increasing y by 2 pi is you're really increasing the function by, you're increasing z by 2 pi I. Okay, if you're increasing y by 2 pi, you're increasing z by 2 pi I. Okay, so that's periodic there. Also, you have a lot of stuff that makes sense. Is this, there's the exponential function is never 0. The derivative of the exponential function is itself. That's interesting. And then you have this piece right here. The magnitude is actually the exponential of the real part, which you kind of know that the magnitude of this is going to be just the r part. Okay, which is e to the x, which x is the real part of z. Okay, so there's that. And then there's the periodic part. Let's take a look at the next page. This is an interesting way to look at the exponential function. So once again, exponential function of z, or rather x plus iy, is equal to e to the x, e to the iy. Okay, so where to begin here? If you, let's start here on 0 right here. So if your real numbers, right here, then the line where there's no imaginary part, so the y's are 0, so you just have e to the x. Then what you're going to get is this piece right here. Okay, as you go back this way towards negative infinity, so as x is going to negative infinity, then you're getting closer and closer to the 0. Right here. This is 0 right here. And then as you go this way, it blows up to infinity. So that means you're just going to keep going out further and further along this array. And then as you increase x, you know, if you're really small over here, then it's not increasing by very much. And in fact, like if you were to cut it off right there, then all of this going back forever would be just go from here to here, if that's one. Would just be go from there to there. All that forever. And then this forever going this way would be, I would be forever this way. Okay. If you increase this by, let's say you increase this by pi over 3, for example. Okay, so we have this one right here, pi over 3. Then that's actually going to go out this way. Okay, so pi over 3 is going to be this. Again, if you're over here, then you're going to be close to the 0. And as you go out this way, then you're going to infinity. You're going out further along this array. And then, of course, this one's going to map to here, and this lower one's going to map to there, and the upper one's going to map to that one. Okay. Now, if you take vertical lines, so like let's say here we have the vertical line at 0. Okay, so here we're setting x equal to 0. Okay, so if we have x equals 0, then we're just having exp of, so x is 0, then that was just going to be exp of iy. There's going to be e to the iy. Okay, so this red one is going to, and this has modulus 1. So this red one's going to be going around this circle here of radius 1. Yeah. And this point here, or rather this point here where they intersect, is going to map to this point here where these two intersect, where the red and the blue intersect. Okay, so the blue lines go to these rays. The red vertical lines go to these circles. So if you have, wait a minute, I mixed up. Ooh. Just a second, I'm gonna try to fix this. I mapped it to the wrong one. Okay, so this one maps to this one. And then where they intersect maps to here. Okay, this line maps to this one. This line segment. Okay, now, if you start at 0, right here, the origin. No, the origin's right here. Yeah, the origin. As you go up, you're going to go around the circle this way, clockwise. As you go down, you're going backwards around the circle. Now, here, there's something called the fundamental strip. Okay, and that would be the set of x plus iy such that y is between negative pi and pi. Okay, and that's called the fundamental strip. And they've kind of like, if you were to cut it off, say right here, around there, and up here at pi. So pi is, let's say this is pi, and this is negative pi I. So the fundamental strip says that the lower half is going to be strictly graded, a strict inequality. So you're not including this lower line down here. And then this upper half is less than or equal to. So you are including this. Okay, so all this and everything in between that goes on. So this fundamental strip goes on. So this is pi, or pi I, and this is negative pi I. Then this fundamental strip goes on forever. Right here. If you restrict the domain to just the fundamental strip, then this maps to the whole complex plane minus the origin. Okay, so there's nothing you can put in, just like with real numbers, you can't put anything in to get 0, so 0 is excluded. But this whole strip gets mapped to the entire complex plane minus the origin. And so the reason we do the fundamental strip, it also has to do with the fact that the exponential function is periodic and going up and down. So what that means in this context is that if you have, say, a point right here, if you subtract 2 pi from that point, then right there, those 2 points are going to map the same. This function is going to map both of these points to the same value. And if you go up another 2 pi, then all three of those points get mapped to the same value by the exponential function. Okay, because the x's are all the same, so that part's going to be the same for all three, and then but then the y is different by 2 pi, so they're all going to be the same too because we're plugging them into the cosine and sine. All right, so that is the exponential function. Okay, now let's get to the sine and the cosine, the complex sine and cosine functions. Okay, and they're defined this way. So sine z is 1 over 2i times the exponential function of iz minus the exponential function of negative iz. And cosine z is this. Okay, now again, some textbooks, or every single other textbook I've seen, or I don't know, I haven't seen very many textbooks stuff, they'll define cosine to be 1 minus z squared over 2 factorial plus z fourth over 4 factorial minus and so on. And they'll define sine z to be z minus z cubed over 3 factorial plus z to the 5th or 5 factorial, so on. I can see the logic in defining it this way because we haven't gotten to these infinite series yet, so that's probably a good thing to define it this way. But later on, and then these are like, if you remember your calculus 2, these are just the formulas for cosine and sine from calculus 2 for the Maclaurin series expansions. Okay, so those are the signs right there. So something else we can do. So let's take a look at this. Let's just take a look at this for a second. Okay, so sine of x plus iy is equal to 1/2 the exponential function of x plus iy wait, no. 1 over 2i, sorry. The exponential function of, I think I was copying out from the wrong formula, sorry about that. I times z, right? So I times x plus iy minus the exponential function of negative iz, so that's negative I times x plus iy. Okay, so if we simplify this, here's what happens. So here we have exp. We can just go ahead and write that as e to the. If we distribute the I, we get, let's see, negative y squared would be the real part, and then the imaginary part will be e to the ix, so e to the ix. Okay, and then this one right here, the real part is negative I squared y, so that's positive y, so that's e to the, I don't know why I got the square, to tell you the truth. I don't know where that came from. I'll erase it. Okay, so negative I squared y, so that's going to actually be positive y. And then this is e to the negative ix, negative ix, like that. Okay, so that's what we have there. And then 1 over 2i. You guys remember what e to the ix is? E to the ix. Oh well, it's cosine x plus I sine x. So it's just a theta replaced with an x, right? And it's e to the y, and then this one is going to be cosine of negative x plus I sine of negative x. Okay. So 1 over 2i, and then we have e to the negative y cosine x plus I e to the negative y sine x minus e to the y cosine x. Because so cosine x, negative x is equal to cosine of x, right? So that just goes away. And then this negative comes out here, like that. Okay. So that's minus e to the y cosine x. And then you have these two minuses here, so that's plus e to the y I sine of positive x. Okay. So now, whoa, something's, come on, man. My thing went crazy. Okay. So let's put the signs up into one piece. And so we can factor in, let's just look at these two terms here. We can factor an I sine x out, right? It's still gonna be over 2i as we pull it out of there. But the i's are gonna cancel, so that's good. And then we'll still have though e to the negative y plus e to the y. But let's write it this way, e to the y plus e to the negative y. And then the cosines, that's also going to be over 2i. That's going to, when we factor those out, let's see here. You're going to get negative e to the y plus e to the negative y. Okay, so we have, I can rearrange things here. Like that. This one, remember that 1 over I is actually equal to negative I. So they change that to a negative I. So, but we distribute the negative into here. Okay, does anybody recognize what this and this are?
Sinh.
Yes, great. This is cosh of y. And this is sinh y. Okay. Okay, so this is another way. This is a very useful way to look at the sign. This is the sine of z. Okay. If you have the real parts x and the imaginary parts y, this is the sign right here. And this is a very useful way to look at it. That appears in the homework. Let me show you. Right here. In fact, you're supposed to show these two right here, and we just showed the first one. Okay, so you get to do the same thing with the cosine. We just showed this first formula. Okay, and this can help. This can help with things like this, like number 32. Prove that the zeros of sine zero are all real valued. So you like look at this right here and say, okay, how is this going to be 0? And how can this be 0? Under what conditions? Okay, the cosh is never 0, by the way. The cosh is never 0. The sinh is sometimes 0. Or sinh is 0 when only when y is 0. I'm sorry. The sinh is 0 only when y is 0. The cosh is never 0. Okay, so you can use that information to do number 3. The number 32. I'm sorry. That can be helpful. I'm just giving you a hint there. Okay. Now, you guys remember from trigonometry, was one of your funnest things going through all those identities? and being like, whoa, there's like so many identities. This is really awesome. Were you guys thinking that when you were in trigonometry and being like, I hope there's more identities? Or what new identities will we learn today? And I love memorizing identities. Is that what you guys thought when you were in trigonometry? Well, here's more identities. Check it out. Check this out. This one holds for complex numbers too. Wow, who would have thunk? And then they're periodic with sine 2 pi, and the tangent, and the other thing is, so tangent is just defined to be sine over cosine, and so on. The derivative of the sine is the cosine. Derivative of the cosine is negative sine. All kinds of identities that come over. Okay, but note these ones are really important. Okay, now they do this hyperbolic sine, cosines, and all that, but honestly, I think just know that those exist. You don't have to refer back to them. Okay, let's take a look at logarithms and complex exponentials. Okay, so the logarithm and exponential function are inverses of each other. And this is what it means to be inverses of each other. That if you take the composition of, so like, if you take the composition of the function with its inverse, you're just going to get the original thing back, right? In this case, it's a z, so I guess that I should have put a z there. And that's all this is saying. But then the other one is that f of f inverse of z is also z. Okay, so the logarithm is the closest that we can come to an inverse of the complex exponential. There is a big major problem with that, but I mean that's what it is. But it's also like maybe it's not so much a problem as just kind of an interesting feature. So the logarithm being the inverse of the exponential function. So first of all, the biggest problem with the exponential function is that it's not one-to-one. Okay, so that's the biggest problem. And so how can you find it? How can you have an inverse of a function that's not one-to-one? Well, you restrict it. You restrict the domain to where it is one-to-one. And so the main thing we do is restrict the domain of the exponential function. Or I should say, that's one option. That's one option. And typically, what we do is you restrict it to the fundamental strip. Okay, so that is x plus iy, such that y is between negative pi and pi. Okay, and that's exactly what they're doing right there. Right there. So you're restricting the exponential function to this set right here. Okay, then this right here, this function here, becomes the inverse. This is the inverse of the exponential function of z restricted to this on here. So this is the inverse of that. And it's called the principal logarithm. Okay, so principal logarithm or so the principal logarithm or the principal value of the logarithm. Okay, now you'll also remember that the argument of a complex number, okay, so argument of z is the angle with the positive real axis, right? Okay, but the principal value of the argument would be the value between negative pi and pi would be this value here. Okay, so this is the principal value of, well, not right there. Okay, so the principal value of the argument. The principal value of the argument would be the theta that's between negative pi and pi. Okay. So the principal argument would also reflect this right here. Principal argument. Okay, so they have a few examples of what they've calculated right here. Let's do this. Let's start with the value. Let's say z equals, we'll say 1 plus I. Okay, so what's the exponential function of 1 plus I? So that would be the exponential function of, that would be e to the 1 times e to the I. Oh dear, that's weird. Maybe this is a really bad example. Cosine of 1 plus I sine 1. Whoa. Am I regretting this? I'm regretting this. Oh well. Okay, now, what if we took the principal value of the logarithm of this e times e to the I? Okay, so according to this formula, it's going to be the natural logarithm of the absolute value, or the modulus of e times e to the I, plus I times the argument of e times e to the I. Okay, so what is the modulus of e times e to the I? What's this value going to be here? Anybody know?
Is that log?
Just this. Yeah, this is logarithm.
Oh, e to the 1 plus I.
Yes, it's e to the 1. Okay, so it's just, what the? Oh my goodness. This is like being, what the? Oh, dang it. This is out of control. Hold on. Whoa, this is really out of control. I think there we go. Let me do that. This is really acting weird. Erased everything. Dang it. Come on. Behave yourself. Oh, dang. Come on. So just E. Without the absolute values, though. hold on, let me, this is just like doing really, really weird. So let me just save this and close it really quick. I'm just going to close that program and open it up in just a second. Okay. So hopefully it's the program and not my writing tablet. Okay, so we're the principal value of the logarithm. So that's equal to the natural log of e. That's just e. And then what's the argument of this? Dang. The argument, so e to the I would be dang, I'm confused. Oh, I see. The argument is just going to be 1 because this e to the I theta is 1. So the argument is just 1. And this is just going to be e. No, that's just going to be 1. I'm sorry. Log of e is 1, and this is I. Okay, so the point is that if you start with a z, you take the exponential function of that z, and then as long as the z originally has this imaginary part is between negative pi and pi, then when you plug it back through the principal value of the logarithm, you'll get back the original. Okay, so that's the point of that. Okay, so let's see here. This looks like a good place to stop for the day. So we just barely introduced the logarithm, not just the logarithm. So LOG, that is kind of like the natural logarithm. In complex numbers, there's just one logarithm. You don't have different bases. And the interesting thing is, I guess maybe you guys ever told that you can't take logs of negative numbers? You ever told that? Said, you're not allowed to take logs of negative numbers. Has anybody ever told you that?
Yeah.
Yeah,
There are
okay.
no numbers.
Yeah, you can take the log of a negative number. Well, actually, you can now. After tomorrow's class, you'll be able to do it pretty well, hopefully. So, everybody have a great day. Unless there's any questions before we finish up. I do want to say, though, that, let's see, not tomorrow, on Friday, because today's Wednesday, on Friday, we will finish off chapter 3, and then perhaps we'll do some kind of a little bit of review. And then on Monday and Tuesday next week, we have exam 1. So you can either take it Monday or Tuesday, and then in class on Monday, we'll have a brief review of some of the things that we've covered so far in chapters 1 through 3. Okay? So any questions about any of that?
No.
No.
Can I ask again, just to make sure? E times e to the I equals to 1. Is that What do you mean? Here?
E to the I, right here.
No.
E to the I is
Um,
cosine 1 plus I sine 1. But
Like,
the argument of e to the I is 1. Okay, so well, let me clarify that, okay? I'll clarify that really quick. Here's how you can tell. Okay, so if theta is between negative pi and pi, then the argument of e to the I theta is theta. Okay, so that since that's a 1i, the argument is 1. Now, here's where it gets a little bit tricky. When theta is not between negative pi and pi. So let's say so you're looking at the principal value of the argument of e to the we'll say 3 pi I. Okay, so 3 pi is going to be, you go around once and then all the way back to here, right? That's actually just going to be pi, because 3 pi is the same angle as pi. Okay, so this is the angle, but to be the principal value, you want the angle between negative pi and pi. Okay, so principal value is going to be an angle between here and here. So either if it's up here, then your angle, you're going to measure this way. If it's an angle down here or anywhere down here, then you're going to measure going down this way in the negative direction. Okay. Okay, so any other quick questions that you want to get resolved before we finish up?
how about Ln? How come Ln of e times e to the I equals to Ln of e?
Well, how come this is this?
Uh-huh.
Because we're taking the modulus.
Oh, okay.
So, yeah, so if you have the modulus of r e to the I theta, that's equal to r. So if you have the modulus of e to the x times e to the something times y or iy or whatever, that's just going to be e to the x. Okay, so in other words, if you have a piece like this or like that, you know, e to the I something, e to the I something, then the modulus of that piece is just going to be 1. Okay, now how do we know that? Well, because it's the square root of, wait, I'm sorry, I jumped ahead a little bit. So this is cosine of y plus I sine y, right? So the modulus is going to be the square root of cosine squared y plus sine squared y, which is 1.